Hi there, good afternoon. Like I promised before, we are going to talk about Riemann integral today. And the last time we went over the basics, and so we are going to immediately jump into upper and lower Riemann sum. Okay, so this is Riemann integral. And for the purpose of our discussion, I'm just going to sketch a curve like this. Let's say this is some function y is equal to fx. And let's say it's bounded over, all right, 0 to 1. And let's take a general partition, sub-interval I mean as well. So this is going to be xi minus 1, x sub I. X and y over here we have 0. And in my last video, we went over what we call the infimum and the supremum. So I'm just going to talk about that just to recap the idea and use it to find the upper and lower Riemann sum. So what we have then, this value over here is the function value, the value of this point x for that function, and it was denoted by small mr because this is what we call the infimum. So infimum of x, and then we had also had this point over here was the capital MR, and this was the supremum of f. So we have two things here, the infimum of x and the supremum of x. What is the infimum of x? What does that mean basically? So let's say this is my curve, okay? When you look at this curve is here. This point here seems to be the last point. If I take the curve from here all the way to here, that seems to be the last point. And every point below it is lower. So this is the greatest lower bound. I would say this is the greatest lower bound. So the infimum, okay, infimum of fx denoted by the greatest lower bound. And how do we find the infimum of of fx? So to be able to find the infimum of fx, we need actually the function values. This value here is going to be substituted into the function. And so the infimum of fx, you just call it like this, so infimum, okay, of f. All right, so I would say infimum dot f, where x belongs to x into sub I minus 1 xi. This infimum is given by now if I were to take the infimum, what I mean by this, the infimum of fx, okay, and I want to use that infimum to find what we call here the lower Riemann sum. So I'm talking about the lower Riemann sum. Now we all should know what is the lower Riemann sum. You see, under that curve we have rectangles, and those rectangles, they are below the curve. So that's the lower Riemann sum. The lower Riemann sum is the sum of all the areas which of those rectangles which is below the curve that approximate to the area under the curve itself. So if I were to redraw this, right, let me just show you where the infimum is. I'm going to start from this point here. Let's just say the point is here, and then you go like this, and a second point here, go like this, third point here, you go like this, you get another point here. You can see the pattern. If I were to, right, so this is one rectangle, that's the second one, the third one, and this goes, sorry, this one would be actually, sorry, over here, right. So here we are. All right. So as can be seen, again, like I've just mentioned here, these are rectangles that are below the curve, and therefore the areas of those rectangles, if you take the sum of the areas of those rectangles, each one of them has an area, and you add them up, you're going to come to an area which is approximately reaching the area under the curve, the Riemann, the lower Riemann integral. Okay, so but we're not using integration as such because we're dealing with Riemann integral here. So what we're going to do now, how do we find the area of a rectangle? Basically, we say the width multiplied by the height. So the width is actually those here, 1, 2, 3. Now let's say this is bounded over, let's say, 0 and 1. So what would be the width of each of those rectangles? So the width of each of those rectangles is going to be delta xr, or delta xi if you want. Okay, let me just put it delta xi. Why do I not write it over here? So the width, no, let's say over here. The width of each, or general one, the width of each of those rectangles is going to be equal to delta xi. And so delta xi, or delta xr, whatever for that matter, is 1 minus 0 divided by the number of intervals, so that becomes 1 over n. So we are going to take the width multiplied by the height, so 1 over n. This curve is a monotonically increasing function. Now you can have curve where it's a monotonically decreasing function. So if I want the area of this rectangle here, okay, the functional values of x over here will be given by this left endpoint. So I'm going to take each left endpoint. So you're going to take each left endpoint for fx. I mean fx, over here it's fx I minus 1. You're going to take this value here and you're going to substitute into this function, whatever that function may be. It could be an exponential function, a trigonometric function for that matter, whatever function it is. You just take the lower, you just take this value of x here for the infimum, and you just substitute it into the function to get that height that you need to be able to calculate the area of that rectangle and take the sum of it. So the infimum of f is this, but then again, what we're going to do now, we're going to try and compute the lower, okay, Riemann sum. Now the lower Riemann sum, let me just put it as Ln, which is the lower Riemann sum, okay, denoted by Ln. So lower Riemann sum is going to be, like we said, the sum of the areas of all those rectangles below the curve. So the sum with x, with I going from 1 to n, all right, and 1 over n multiply, 1 over n is the width, so that's delta xi, okay, we can say delta xi, okay, multiply by small mr. Why small mr? Because when you substitute this into the function, you can take the infimum. We are taking the infimum because we need the lower sum, not the upper sum. For the time being. So what is this basically? What is the sum of lower sum, okay, of all of that? So how do we get that? So you can take, first of all, if I is equal to 1, it's going to be x1 m1 small m1 plus the delta x2 small m2 plus delta x3 small m3 plus delta xr small mr. So this is how we go about and compute the lower sum, the lower Riemann sum for a function. Okay, and if there's nothing else, now we can move on to the upper Riemann sum. Okay, so upper Riemann sum, very interesting. It's going to be the opposite of everything. So instead of the infimum, now we're going to be taking the supremum. So let me just write it in bold here, the upper Riemann sum. The upper Riemann sum, I'm going to denote it by UN over here. Very interestingly, so we're going to take UN is equal to the sum, okay, with I going from 1 to n, and this time xi, okay, or xr for that matter. You can just put it xr if you want, because I would be just 1 point, but r, generally speaking, times the height again. But what is the height? Now remember, this was 1 over n over here, so we could actually go further in writing this in a nice form. Delta xi, which is 1 over n, so you're going to say 1 over n into mr. And mr is this one here, okay, for the lower Riemann sum. So if this was to be expanded further, so instead of mr, you could go for f of x into f of x sub I minus 1. Okay, so in the same way, mosquito here. All right, in the same way, we are going to try to compute the upper Riemann sum. Now, how does the upper Riemann sum looks like from this graph? Okay, so let me just, this was actually for the lower Riemann sum. Now let's move on and go to the upper Riemann sum. Upper Riemann sum. Now for that, I'm going to take the same curve, but this time we're going to take the rectangles whose heights lie above the curve. So how do we do this? So remember, we took the left-hand point. What was the left-hand point? Was it? All right. So whatever it was. Okay, we took the left-hand points to get the. Now we're going to take the right-hand point. So I'm going to say, if I have a height over here, and I want the rectangle which is above this curve, it's going to be here. Okay, and then you're going to move on like this. This curve is going like this here. Okay. All right. So as you can see now, these rectangles, they tend to be higher. Okay, so the curve goes on like this, and so let me just so here. Okay, I'm very bad at drawing over here. Doesn't really matter. It doesn't really matter as long as you get the idea of what I'm talking, what I'm driving at. You can see all these rectangles over here. They have heights which is above the curve. So that's the upper Riemann sum. And for the upper Riemann sum, we're going to take the right endpoint. So I'm going to say this point over here. This point is this one over here. So this is actually, if I take this point here, I'm just going to take, this is my xi, and this is my big capital MR. So that's the supremum. So we're going to take the supremum, okay? And for the supremum of fx, that's what is the supremum basically. If you look at this curve, okay, and for that matter, you can get this point here, which is maybe the starting point. So that's the lower bound. And if you go further, okay, you have all lower bound becoming greater than this. So this is the lowest, all the points going up will be the upper bound. So that's the lowest upper bound. Lowest upper bound. So the supremum of fx, let's talk about supremum, okay, of f is actually the lowest upper bound. Okay, lowest upper bound. And how do we do this? We were calculating the upper Riemann sum would be the lowest upper bound times the width. And the lowest upper bound is this value here. That's going to give you the lowest upper bound. This value here will be substituted, okay, into fx. And that's going to give you this value mr, capital MR. So we're going to multiply this by capital MR. And again, we understand that this is basically, okay, capital MR is going to be equal to delta x1 capital M1 plus delta x2 capital M2 plus delta x3 capital M3 plus delta XR capital MR. And this is how we go about and find the upper Riemann sum. Well, I hope this gives you an idea actually of what we mean, so as to clear the confusion, between lower Riemann sum and upper Riemann sum. And there's nothing more to it, except that this is going to lead us further into calculating the upper Riemann integral as well as the lower Riemann integral. This is a very important concept, and as such, it's the basics of Riemann integral again. So the next time I'm going to try to go over this again with an example. When I say an example, I'm going to take a question from the Further Maths Advanced Level Code 9231 from one of the latest papers, October 2024. And we're going to be looking at a question where we have to calculate the upper bound and the lower bound. So the upper Riemann sum and the lower Riemann sum, as well as some questions set out by the examiner in that same question there. For instance, once you've calculated the upper bound and the lower bound, they will ask you, to prove that the upper bound minus the lower bound should be equal to 0. Or maybe as n, the value of n, or the value of the number of rectangles tends to infinity, what's going to happen to the function, and things like that. So the value of the function, actually. And I can't wait to actually upload a video like this. And so we're going to be looking at a question, and it's going to be a bit of a lengthy question as well. Take care. Thank you for your attention. I hope that this has been of some help to you. All right.